Hello everyone, this is Sinan Ertemel. Welcome to my fourth lecture, which is about iterated elimination of dominated strategies and sophisticated equilibrium. So I would like to illustrate our second solution concept via an example which occurred in history, the Battle of the Bismarck Sea. This is a war in the Pacific Theater in 1943. Where the Japanese Navy is going to transport its troops across the Bismarck Sea to New Guinea. And there are two routes that Japan can take, north and south. North route takes 2 days and south 3 days. And the American Navy would like to stop that troops, right? But it's a simultaneous game, so neither country knows about the moves of the other country. So the American admiral has two options. He can send the warplanes to the north route or south route. But if he picks the wrong route, then he's gonna lose 1 day. Like one less day of bombing. So this game is a two-person zero-sum game. So if America is bombing, let's say 2 days, it's gonna be +2 for America, and for Japan, it's gonna be -2. So if America picks the wrong route, the bombing days will be reduced by 1. Accordingly, let's create our payoff matrix. US is the role player, the blue player, and Japan is the column player, which is the red player. So if they both go to the north, America is going to be bombing for 2 days, +2 and -2. If America goes to north and Japan goes to south, then among 3 days, America is going to bomb only 2 days. So 1 day is going to be for rerouting. So the payoff will be America +2 and Japan -2. What about US going south and Japan is going north? Then instead of 2 days, America is bombing for 1 day only. So the payoffs are +1 and -1. And finally, if both of them go to the south route, then America will bomb for 3 days, +3 and -3. So first of all, here, one player, in particular America, does not have any dominant strategy. There is no particular strategy which is always better for America. Let's look at north. If America goes north, he's gonna get 2, regardless. If Japan goes to north, +2, south, +2. However, if America goes to south, then it's gonna be a risky action, because he can either get +1 or +3. So we don't have any strict domination. So the first solution concept, which is dominant strategy equilibrium, in which everybody plays the dominant strategy, that doesn't work here. Because America does not have any dominant strategy. As theorists, we are looking for relaxation of the axioms so that to arrive to a meaningful, reasonable solution concept. And here the way that we will do it is look at the other players and see whether the other player have either dominant or dominated strategy, and we will argue that rationality says that no player would ever play any dominated strategy. So if there is a dominated strategy, we will eliminate that from the game. And then we will look at the reduced game, and in the reduced game we will check whether any strategy is dominated and so on, until we arrive to any particular outcome or outcomes. So if we look at Japan, we have a weakly domination here. You see, Japan, if goes to north, he will get either -2 or -1. However, if he goes to south, he will get -2 or -3. So north weakly dominates south, because sometimes you get the same payoff, -2, -2, but if you go north, you get -1 compared to -3 if US goes to north. So you see, in this case, we have a weakly dominant strategy. So a rational Japan, which is presumably commanded by a rational admiral, his name is Imamura. So rationality assumption is important, that who is playing the game. So in general, when we are talking about army, navy generals, we expect them to have some strategic training. So, and the minimum idea of rationality in this context is do not play any dominated strategy. So we expect Japanese Admiral Imamura not to take the south route. He would take the north route. Okay, so how can I proceed from here? Japan is rational, America is rational, but do I have to impose something extra? In order to arrive at a solution, we better assume something else. America is rational, Japan is rational, and America knows that Japan is rational. So America knows that Japanese Navy does not go to south, instead to north. So we have the following reduced game, where it is 2-by-1 matrix. So what would America do in this case? If America goes to north, he will get +2, and if he goes to south, it's going to be +1. As American Admiral Kenny is rational as well, he's going to take the north route. So we end up with both America and Japan go to north route. It's a single outcome, and that's our sophisticated equilibrium. So basically, we arrive to this particular outcome, the sophisticated equilibrium outcome, by iterated elimination of dominated strategies. So the idea of the sophisticated equilibrium rests on this fact. And moreover, we arrive to a single outcome. So we say that the game is dominance solvable if by eliminating of dominated strategies, we reach to a single outcome. And we will argue that this is a compelling outcome because each individual is rational and they know that they are rational, and sometimes we need to impose some other layers as well. They know that they are rational. But we don't have to go all the way until infinity. Here, 2 steps were enough to reach to an outcome. So that's the concept of sophisticated equilibrium. In the next lecture, I will argue the limitations of the rationality axiom by introducing a very celebrated game, which is Keynes's beauty contest, which we will illustrate by playing a guessing game. Thank you very much, and see you all in the next lecture.